Hello everyone. Yeah, so we got stuck a bit and I was able to identify what was the issue. I think few of you might have already been able to figure out where the issue was. So I think w- the problem or the thing that I was doing was trying to differentiate this equation with respect to this, but actually what it was supposed to be was this equation with respect to this equation. So um, it means with respect to count sum inverse, okay, not count sum. So this is d sum, right? So this is not d sum, this should be d sum minus 1. That was the intention. So anyway, you can see, so x into this is the count sum inverse that has to be differentiated with respect to d with respect to count sum inverse. That was the intention. So what they did was they took it as u. Okay, they defined it as u, so x into u. Obviously we are dividing dx into u by u, so x comes out and output answer is x, and that was the reason why you see just counts here. So nothing of these comes here. Okay, this should be counts multiplied by the probability of d probes that is already there, and then we sum it across the gradients, because that's how the gradient for this works. So we'll get this here, and now we are getting it as a true. So you understood it, right? So I was doing this, but rather than it should be d sum, it should be something like this. Okay, and this also can be written as, so that's it. So this is x u, and this is by u. So obviously dxu by du will be x, so you will just see x coming out of it. So that was the reason why it is only counts, and then we multiply it with um, the output layer probability, and then we sum it across. So that was it. I don't know if you had to share anything else.
And let me erase this. Now let's also backpropagate into counts, which is the other variable here.
Okay, we reached till this point. Now we need to calculate the counts as well. So we need to be pretty wary of what we want to calculate here. So this will be again um, so some inverse and everything got calculated with respect to count. Oh no, with respect to this we calculate, right? Now it should be with respect to count sum, yeah. So this is what we need to calculate. So this is count sum. So It is 1 by count sum. Okay. So what we need to calculate is d counts by the local derivative. That will be d count. Oh no, sorry. D count sum. That is, sorry. So we need to calculate this individual. Okay. And this is d count sum by. Actually, it should not. We should not. I mean, these two are a bit obviously different, but I think you are able to understand what I'm trying to do here. If there is any doubt, right, please let me know. This with respect to this. The count sum inverse, this is what we calculated here, so we will plug it in directly here. But here what we are trying to do is the local gradient is what we are trying to calculate here. Okay, so decount sum inverse, so we will focus upon this here. So this will be equal to d of uh, mm, yeah, decount sum, that will be equal to, so this is like 1 by x with respect to x. So usually what happens, the power comes in between. This is somewhat like this itself, right? 1 by x, the one we were doing. And the power increases by +1, so it should be -1 by count sum whole square, and then whatever this is here, correct? So okay, count sum, so -1 into count sum whole square minus count sum here is this individual, so this should also be 32 cross 1. So we have 32 rows, each having one column. That is a summation of all of those. Okay, so if I have to see, 0th is 10.9. Okay, sorry, that's it. What we do is I just wanna square it up. ऐसा करें, कि 1 by 1000, somewhat like that. Is this answer? I'm not sure, but I believe that's how it should be. Oh, sorry. Mm, near about same. So we'll do this, and if I do a -1 and 2, it gets a negative number. This would be 32 cross 1 into this individual, and that would be the count sum, and we can do a comparison as well. Oops. Oh, sorry. That was fine. Now we need to calculate the counts. So this will be again equal to d count by d count sum, and this should be this way. Okay. D count is 32 cross 27, so that's how we want the response to be. So D count is anyway the summation. Okay. Down, yeah. Score sum. It is sum of means count sum is equal to x plus y plus z, and that's it, and count let it be x. So d of that by this would be 1. Okay, means df this by dx will be 1. So this is 1. The same will get percolated there, but I think then we need to broadcast it because it has to come in this shape. Let me see if that works. Where it went, man? Ah, this we need to broadcast, right? Hmm. I think and we can some is happening, right? The same gets percolated whole across. Yeah. Hmm. From my perspective, that's what it should have been. It looks fine to me. That's what I'm getting, no? First value is different here. Okay. So some of the values are changing inside of this. All are not equal. See here. Oh, sorry. If you see this right here is a change. It's -0.
To create props. So from props to count sum inf, we just did that. Let's go into counts as well. So dcounts will be
Not sure.
exact match. So this derivative is exactly correct. Counts, which is the other variable here to create props, will be, so therefore it's count sum inf is 32 by 1, dprobs is 32 by 27. So those will broadcast fine and will give us dcounts. There's no additional summation required here. There will be a and will give us dcounts. There's no additional summation required here. There will be a broadcasting that does decount. Now count sum inf is 32 by 1, d here to create props. So from props to count sum inf, we just did that. Let's go into counts as well. So dcounts will be, dcounts is our A, so dc by dA is just B. So therefore it's count sum inf, and then times chain rule dprobs. Now count sum inf is 32 by 1, dprobs is 32 by 27. So those will broadcast fine and will give us dcounts. There's no additional summation required.
Okay, I did a mistake again here. Decounts mean d loss by decounts. Okay. So count impacts decounts sum. Okay. Means I want to use this. So decount sum by decounts into d loss by decounts. I keep getting confused between these two. Um, okay, sorry. Yeah. So impact of d counts on d sum, and we have already calculated the impact of d count sum on d loss. So this is already calculated. That is, yeah, this is already calculated here. So we need to calculate this part. Count sum by d counts. Ah, okay, okay. I got it. I got it. So here is one good part that I learned as of now. So the thing is, if you remember the chain rule, right? Let me see if I can show you. Um, is there any complicated structure to it? Yeah, something like this. So, you can think of this as the counts, and this you can think of it as, what was the other one? Where it went? Yeah. So one is counts, one is count sum inverse. So it can be count sum inverse, and this can be counts. So these two are multiplying you to give an output. So in back propagation, if you remember right, when we sit here, we calculate the gradient for this and the gradient for this, whichever are, we form that tree structure, okay? So that's where we need to calculate decount. So it is something like how counts is impacting probs, and then how probs is impacting loss. So this should be broken as d probs, and that's the reason we used to form this tree here. No, where is the code for that? Yeah, this build topology used to be created one after the other. That's how we wanted to traverse the tree. So d probs deep probes, how count impacts deep probes, and then how deep probes impact um, how d probs impact d loss. Okay, so this is already calculated, which is d probs, that is here. We need to just calculate this part, and probs equal to count into count sum inverse. So this will be equal to either some multiplication, so we'll get this thing. So here it will come as this thing into d probs, that is equal to, yeah, d probs, so obviously, okay. So
required here. There will be a broadcasting that happens in this multiply here because count sum inv needs to be replicated again to correctly multiply dprobs. But that's going to get the correct result. So as far as this single operation is concerned, so we've backpropagated from probs to counts, but we can't actually check the derivative of counts. I have it much later on, and the reason for that is because count sum inv depends on counts. And so there's a second branch here that we have to finish, because count sum inv backpropagates into count sum, and count sum will backpropagate into counts. And so counts is a node that's being used twice. It's used right here into probs, and it goes through this other branch through count sum inv. So even though we calculated the first contribution of it, we still have to calculate the second contribution of it later. Okay, so we're continuing with this branch. We have the derivative for count sum inv. Now we want the derivative of count sum. So d count sum equals, what is the local derivative of this operation? So this is basically an element-wise 1 over counts sum. So count sum raised to the power of -1 is the same as 1 over count sum. If we go to Wolfram alpha, we see that x to the -1, d by dx of it, is basically negative x to the -2. Right? Negative 1 over x squared is the same as negative x to the -2.
okay,
So d count sum here will be local derivative is going to be negative counts sum to the -2. That's the local derivative times chain rule, which is d count sum inv. So that's d count sum. Let's uncomment this and check that I'm correct. Okay, so we have perfect equality. And there's no sketchiness going on here with any shapes because these are of the same shape. Okay, next up we want to backpropagate through this line. We have that count sum is count.sum along the rows. So I wrote out some help here. We have to keep in mind that counts, of course, is 32 by 27, and count sum is 32 by 1. So in this backpropagation, we need to take this column of derivatives and transform it into an array of derivatives, two-dimensional array. So what is this operation doing? We're taking some kind of an input, like say a 3 by 3 matrix A, and we are summing up the rows into a column tensor B, B1, B2, B3. That is basically this. So now we have the derivatives of the loss with respect to B, all the elements of B. And now we want the derivative of the loss with respect to all these little a's. So how do the b's depend on the a's is basically what we're after. What is the local derivative of this operation? Well, we can see here that b1 only depends on these elements here. The derivative of b1 with respect to all of these elements down here is 0. But for these elements here, like a11, a12, etc., the local derivative is 1, right? So db1 by da11, for example, is 1. So it's 1, 1, and 1. So when we have the derivative of the loss with respect to b1, the local derivative of b1 with respect to these inputs is 0s here, but it's 1 on these guys. So in the chain rule, we have the local derivative times sort of the derivative of b1. And so because the local derivative is 1 on these three elements, the local derivative multiplying the derivative of b1 will just be the derivative of b1. And so you can look at it as a router. Basically, an addition is a router of gradient. Whatever gradient comes from above, it just gets routed equally to all the elements that participate in that addition. So in this case, the derivative of b1 will just flow equally to the derivative of a11, a12, and a13. So if we have a derivative of all the elements of b, and in this column tensor, which is d counts sum that we've calculated just now, we basically see that what that amounts to is all of these are now flowing to all these elements of A, and they're doing that horizontally. So basically what we want is we want to take the d count sum of size 32 by 1, and we just want to replicate it 27 times horizontally to create 32 by 27 array. So there's many ways to implement this operation. You could, of course, just replicate the tensor. But I think maybe one clean one is that d counts is simply torch.ones like, so just an two-dimensional arrays of ones in the shape of counts, so 32 by 27, times d counts sum. So this way we're letting the broadcasting here basically implement the replication. You can look at it that way. But then we have to also be careful because d counts was already calculated. We calculated it earlier here. And that was just the first branch, and we're now finishing the second branch. So we need to make sure that these gradients add, so plus equals. And then here,
So this will calculate, this will also calculate for this. So two calculations are going to happen because this is impacting two of them. So in the same way, counts was impacting here, so this will be calculated two times. D of counts happen, count sum was also true. Now we are going to calculate this. I think this was a single equation. Yeah. So normally this is what we want to calculate. Okay, so norm digits is impacting counts, count is impacting loss. So this is the general. This is already calculated. Count is equal to e to the power x e to the power x by x. I think it is e to the power x is e to the power x itself. So this thing, right, is equal to this into d counts. So okay, and not all of them are happening, so that's fine. So this will be equal to, let's get the shape of both of them just to make sure they are above. So counts IO dot shape and shape of this individual. Okay, so we can do the division easily. So this will be equal to okay, that is one. So I was able to calculate norm logits as well. After that, again we'll write the same thing. D of counts by D of counts by you know, sorry. Okay. So impact of logit maxes on norm logits into impact of norm logits into norm loss. This has been already calculated up. So this is the value that we want here. So we need to calculate this individual. Okay. Now the norm logits. What is norm logits? Norm logits is logits minus logits maxes. Logits. Oh, sorry. So logits help in two places, here and here. So it's something like this. So logit is helping in one and the other as well. So there needs to be an addition for that. Okay. So T logits will be a bit different. Let's calculate logit maxes, but logits logits right will needs to be calculated. Two additions that needs to happen for this. Yeah, so d of this by this. Okay, this will be equal to 0 minus 1, so it will be -1. So -1, so here it will be equal to -1 into the logic maxes, that's h. So that's it. Okay, and we need to come. Yeah. Logics can't be defined in logic maxes, right? Okay, but we can define logic maxes in terms of what we're defining with logic maxes, right? Yeah, logic can be defined in terms of. I think there might be issue with respect to the shape. Logic maxes how it should be. I got it. So it should be like this. So here it will be 32 by 1. And what we are proposing is something like this. Okay, so that's the chance. So what is happening here is calculating max for each of them. So there is a summation, and there is a logic coming, and there is a subtraction. So if I sit here, if I need to calculate, so I'm getting it where the issue is. You're sitting here on. This is logic maxes. Okay. Max says it broadcasting into 3 and then subtracting it. Okay, so there is a broadcast happening as well. And that broadcast that is happening, there's 3 separate subtractions. Okay. Mm, okay. All of them will get added. So here, load some. That solves the problem. Um, I can help you explain this picture using pictures, but just let me know if you're not able to understand why we are doing the sum. Now it should be 32 cross 1. Yeah. Okay. Yeah. We'll do this in the next session. We have reached till here. Okay. So, bye bye.